Alright, we're going to mainly talk about graphs of functions today. So let's start by talking about how do you graph a function. I know this is probably basic to you, but let's just talk about a few things here. The graph of a function is all ordered pairs that satisfy the function, which means make the function true. So if that's an equation, that means makes the equation true. If it's a verbal statement, it's make the statement true, etc. So here we have a table of values, and this is all we're given about our function f. So let's just go ahead and plot these values here. So we have negative 3 comma 4. And then negative 2 comma negative 2, and 1 comma 3, and 2 comma negative 1, and 3 comma 2. Okay, now we used to do this in class, and then I would come around and look and see what people had written on their paper, and invariably about half the class would have connected these dots in some way, shape, or form. Okay, and the point here today is you don't connect these dots based on what you see in this table, because there might not be any more dots besides what's in this table. Okay. Plus, there are many, many ways to connect the dots if they were connected, and we don't know what manner to do that. Let's go to a quick GeoGebra demonstration. Okay, what we have here is what I'm going to think of as a little machine. That's our function. It's going to work across the x-axis, which is like working across the number line, and it's going to basically take in an x value, and it's going to spit out a y value where it belongs for that x value. And it's going to spit out values every 100th of a unit. So what you're going to see is a lot of dots plotted, but you're not going to see them connected. The idea here is that a function is a collection of dots. And when the dots are plotted so close together, that's when the graph appears to be a solid connected picture. So I'm going to go ahead and animate this slider bar up here, and what you should see is dots being plotted as the machine works across the x-axis. So it's taking in the x value as it goes over it, and it's spitting out the y value that goes with that x value, and a dot's being plotted. Okay, the dots are not connected because the machine is only taking in the x values every 100th of a unit. If we made the machine take in x values quicker than every 100th of a unit, then we might start to see a picture come together. But the idea here is that functions are plotted with dots, points in the plane. Okay, so one of the things that we encounter quite a bit in our courses are functions that are defined in pieces, which means that I have one function that's really several functions with different domains, and those domains do not overlap. A lot of students find these bothersome, but there's really no big deal. Okay. What I want to point out is maybe a simple way to handle these. Okay, let's go ahead and start by noticing what are the different domains given in this piecewise function. Okay, we have one function whose domain is x is less than 2, one function whose domain is x is bigger than 2, and then the middle piece is really just one point, but this is what happens when x is 2. So what's convenient to do, in my opinion, is to draw a barrier where this function splits. So this function splits or changes its domain, changes its personality when x is 2. And so I'm going to go ahead and create a dotted line in the graph. It's not part of the graph, but it's a nice reminder to me that something happens at that spot. Okay, now because I have equations for these functions, and I'm going to make a table of values here for the nice x values, but I'm allowed to connect dots because I could plot more dots if I needed to, besides just these ones in this table. Okay, so if x is negative 3, which function do I use? Well, I use the first one because negative 3 is less than 2. So up until I get to here, okay, I'll use this first function. So we get negative 6 plus 3 is negative 3, and we get negative 4 plus 3, which is negative 1, and we get negative 2 plus 3, which is 1, and we get 0 plus 3, which is 3, and finally we get 2 plus 3, which is 5. Okay, let's pop those dots real quick. So negative 3, negative 3, negative 2, negative 1, negative 1, 1, 0, 3, and 1, 5. Now, as I said, you can connect these dots because there are points in between because we have an equation that defines this function. Now, we can also plot more dots between 1 and 2. but 2 is where this function splits. So here's a little idea that I'd like you to get into your minds, how you handle what happens between 1 and the barrier. Okay, we would like to make a little notation here, okay, that says when x gets close to 2, and I'm going to say gets close to 2 and put a little minus sign above the 2, which means as x gets close to 2 but is less than 2, okay, what does our function do? What does our function get close to? So our function is going to approach some value, hopefully. Okay, now I look at this and I say to myself, if I could plug in 2, if I could plug in almost 2, what almost comes out? Okay, well, if I could plug in 2, I would get out 2 times 2, which is 4, plus 3, which is 7. So your function is going to get very close to 7 when you get close to 2 from the left side. Okay, so I look at this and I see 2 comma 7 would be right here, and so on the barrier I'm going to plot an open circle, okay, which tells me that that is where the first part of this function stops at that open circle. So I'm going to go ahead and get a line. I'm going to connect those dots with a line. And there I have the first part of my function. Now, when x is 2, the function value is 5, so there's a dot on the barrier right there. All right, let's go ahead and get some values for what happens after 2. Remember that this was 5. Okay, so when x is 3, we're going to get 3 squared minus 8, which is 1. And when x is 4, we're going to get 4 squared minus 8, which is 8. So I should have 3 comma 1, which is here. And I also should have 4 comma 8, which is up here. Okay. Now, in a similar manner, I would like to know what does this function, this part of the function, do when you get close to the barrier. So down here, I'm going to write as x approaches 2, but this time from the positive side of 2. Okay, what does the function do? So if I'm bigger than 2, this is my rule. And if x was 2, if I was allowed to plug in 2 for x, okay, what would I get out? I would get 2 squared, which is 4, minus 8, which is negative 4. So that means as I get closer to 2, this will get closer to negative 4, which is down here, and so I'm going to put an open circle. And if I was skilled with the slate, I would try to connect these dots with a curve, because we knew that x squared minus 8 is going to create a parabola. I'm not very skilled with the slate, so I'm not going to try and embarrass myself here. But I can also plot some more dots in between 2 and 3 and 3 and 4 to make the picture more accurate. So a function takes in x values and spits out y values, and as the x value changes, the y values change. And what's an important concept to study is where do functions increase and decrease? And that means where do their y values increase or decrease? So let's come up with a definition for what that means that we can agree on and use all year and into next year. Okay, so let's choose some x values. So let's use x1, and we'll assume that x2 is less than x2. Okay, so for example, x1 might be here and x2 could be here. Okay, so if f of x2 is bigger than f of x1 for all x on an interval, and let's call the interval a to b. These are x values, okay? Then we say f is increasing. Okay, what that means is as the x values get bigger, the y values also get bigger. And that's true for every x value in this interval, or every pair of x values in this interval. If we reverse that, okay, so if f of x1 is greater than f of x2, for all for all x, right, for all x values on an interval, then we say f is decreasing. Basically what that says is As the x values get bigger, the y values continue to get smaller. So if I look at this picture, not very hard to come up with these conclusions, but we would say f is increasing on the intervals a to b and c to d. And f is decreasing on the interval b to c. Okay? And these are bracketed intervals, which means point B is included in both an interval of increase and an interval of decrease. And that's okay, because it fits the definition that we've come up with over here. Okay? What that also means is that this function, okay, may throw you for a loop, may not throw you for a loop, but this is always a healthy debate every year. If this function is called f, then we would say f is increasing from -4 to 1 and from 4 to 8. We don't include this section where it's constant from 1 to 4. Okay? Depending on your definition, that could be included, but then we'd have to alter things that we had in the last slide. So I hope you're good with that. If you're not, we can have a healthy debate about it and discuss the nuances of the definition. Okay, some geography for functions that we're going to talk about from time to time, mainly in calculus, but we'll talk a little bit about them in pre-cal. All right, we have two types of geography to talk about. We have a local or a relative geography. Okay, relative means relative to what's around you in a neighborhood. Okay, and then we have a global or absolute geography. Okay, which means over the entire domain or the entire set of values that we're looking at here. Okay, so let's first look at this point right here. Okay, in a little window, which I'm going to highlight, this is the highest y value in this neighborhood. Okay, so we would call this a local or a relative maximum. Okay, meaning if I consider all x values on either side of that point in a neighborhood, and a neighborhood can be small, that is the highest y value. So it's a local maximum or relative maximum. Similarly, down here, okay, in a neighborhood, okay, this would be considered a local or a relative minimum. Obviously, this would also be a local maximum, this would be a local minimum, and this would be a local maximum. Now, in the entire picture here, okay, if I consider all possible x values in the entire picture, we're going to assume that they stop at these two spots right here, a little bit less than -8 and a little bit bigger than 8. Then this dot right here would be the global maximum. That is the biggest y value in the picture, the biggest y value in the range. Okay, global maximum or absolute maximum. And that means that these 2 points here are not only local minima or relative minima, but they're also absolute minima. They are the smallest y values in this picture. Okay, in pre-cal, we mostly ask you to find these things via a calculator. But if you have the picture, they're easy to find as well. Calculus, we learned some techniques to find these by hand. Okay, now, most of the functions that we study this year are going to be curves, because lines are mainly Algebra 1 topics. They're very easy to talk about. So there are times where we will take 2 points on a function's graph and connect them with a line. This is called a secant line. Okay, so what is a secant line? Okay, a line that connects 2 points on a curve. This has some connection to the other times you've seen the word secant used. You've seen secant used in terms of circles, it was a line that went through a circle and 2 points, and this is kind of like a line that goes through a curve and 2 points. And you've also seen secant used in terms of trig functions, and in the original Greek diagram there was a connection there as well. Okay, what we like to talk about a lot of times is the slope of the secant line. So let's call this point a comma f of a, and let's call this point b comma f of b. And let's calculate the slope of this line. Okay, the slope of this line would be the change in y, or the change in f, if you like, which would be f of b minus f of a, divided by the change in x values, which is b minus a. Now, let's take a look at why this is important to us. Okay, let's take a look at a real life type function that describes something in our world. So this is the graph of t of x. So x is plotted on the horizontal, t is plotted on the vertical. It's a function that measures the number of people in the Toyota Center, where time is measured in minutes. So x is the time, and x is measured in minutes. And t is measured in thousands of people. Okay, so I'll put thousands of people on the vertical axis. Okay, I've shown a portion of the graph, and I have chosen 2 specific points here. So we've got 4 comma 5.25, which means at 4 minutes after, I guess, the game has started, there are 5.25 thousand people in Toyota Center, and at 1 minute after the start of the game, there are 4,000 people in Toyota Center. So I guess people are arriving late to the game. All right, so we have 2 points on the curve. I've connected them with a green line. Let's calculate the slope of that line. So the slope of this line, the slope of the secant line, is going to be 5.25 minus 4 divided by 4 minus 1. Okay, which gives us 1.25 divided by 3. And let's convert this 1.25 to a fraction. That's going to be 5/4. So 5/4 divided by 3, which is 5/12. Okay, so we have this number. It's a slope of this secant line. But this has some units to it. And those units are going to provide us with a meaning for what this number calculates. Okay, so what are the units for the numerator? Well, the numerator was the change in the y values, which are measured in thousands of people. Okay, so I'll put thousands of people, basically people, right? And then the denominator was the change in the x values, which are measured in minutes. So what you've calculated when you calculate the slope of a secant line is a rate. In this case, it's thousands of people per minute, and it's not just the actual rate, because obviously things happened between minute 1 and minute 4.5 that these numbers don't account for, but this is what's called the average rate. Okay, average rate of change of this function. So the average rate of change of what function? T, right, on an interval. Okay, the interval 1 to 4. So this is one way we measure how fast the function changes. We measure on average how fast does it change between 2 points. In calculus, we refine this to find out how fast does it actually change at a specific point in time. Okay, very neat. But for now, this is the best we can do. So let's reiterate so you have it for your notes. The average rate of change of a function on an interval, so we have to have an interval, is the same as the slope of the secant line that connects the 2 endpoints of the interval. So the AROC, average rate of change, of f on AB is the slope of the secant line, which is found by this calculation, f of b minus f of a over b minus a. Okay, this average rate of change is an approximation, right? It's an average for the actual rate of change, which is something you can't quite do till next year in calculus. All right, the smaller the interval, the better the approximation. So this interval was what, 3 minutes long, okay? If I could shrink that interval down, then my average would be a better approximation for the actual rate of change at 1 minute of time. We're going to use this calculation quite a bit, so get comfortable with it and be prepared to use it in the future.